Okay, so elevators and apparent weight. When a person is accelerating upwards or downwards, so you've experienced this before, whether you're riding an elevator and the elevator is going up, or you're riding the elevator from a higher floor down to a lower floor, or you're in a car on a bumpy road. There's a section of the Abbey Mission Highway that before it flooded and they fixed the bump, if you hit that bump fast enough, you feel like you're kind of floating upwards. All of a sudden you feel like you weigh less than you did a second ago. You can feel heavier or feel lighter than you actually are when you experience these upwards or downwards accelerations. Or if you've ever been to Disneyland, something like the Tower of Terror. You're sitting there in the chair and you're waiting, or at the Playland when you're on the elevator and you're sitting there and you're waiting, and all of a sudden you start to fall. You feel a lot lighter. The chair is dropping away beneath you. Are you actually lighter? Well, not necessarily, but you feel it. Your experience of it is different than what it normally is, and that's what we call apparent weight. Apparent weight is your experience of your weight. Now go for a minute. In these situations, although your actual weight, and if you remember what actual weight is the force of gravity acting on you. Gravity doesn't change as long as you are at or near the surface. And I watched another one of those Star Talks that I introduced you guys to a couple days ago. Near the Earth's surface, or is within up to like 100 kilometers from the Earth's surface. So on or near the Earth's surface, your actual weight is the force of gravity acting on you. That does not change. But your apparent weight can change. Apparent weight is how heavy we feel, and it's equal to something supporting you. When do you feel heavier or lighter? Give me an example of when you've experienced this. Here today. So you've experienced this in an elevator. You're standing in the elevator goes up. You feel what in that case? You feel heavier when the elevator goes up. Why? What is acting on you to cause you to rise? Is the rope attached to you in the elevator? So that's not what's causing you to rise. I think you said it before. What is causing, as the elevator goes up, what's bringing you with it? Okay, so what do we call that? What do we call the force that is you standing on the floor of the elevator? Normal force. When the normal force, the only way that you go up in an elevator is because the floor is pushing on you. When you're in contact with the surface, we call that the normal force. So how heavy you feel is equivalent to your experience of the normal force. When the normal force increases, you feel heavier. You're not, but you feel heavier. When the normal force decreases, the thing is trying to fall away from you, you feel lighter. You're not, but you feel that way. So your experience of apparent weight is actually your experience of a changing normal force on you. So we're going to look at the mass, your mass, and a spring scale in an elevator. I want to look at these three questions, and we're going to go ride the elevator. We're going to look at the questions. We're going to go ride the elevator. I want you to think about your experience in the elevator, and then we're going to come back and we're going to fill this in. We're going to go ride the elevator. We'll ride it a bunch, first, second, third floor, first, third, well, as much as we can ride the elevator before someone stops us. And we are going to describe, what I want you guys to see if you can identify is 2 times when you feel heavier than you do now, just sitting at your desk. I want you to describe 2 times when you feel lighter, and 3 times when your apparent mass and your actual mass or your actual weight is equal. When do you stop feeling the weirdness? So let's go ride the elevator. And I'm going to bring a scale with us. Okay, we'll ballpark it. Cool, thank you. 150-ish. Okay, so just gonna make a note here. Where do I want to put the note? Let's go up here. So here day is approximately 150 pounds. On the way up, as we were rising, that's when you felt heavier, yeah? I don't know, it hit maybe 158. On the way down, it hit maybe 142. We're going to use that information in a second here. So Vine described it 2 times when the mass appeared heavier than normal was moving up from rest, and moving down and stopping. Both of these situations actually are the same. We talked about it in the elevator. We'll formalize it here. In both of these scenarios, acceleration is happening which way? Yes, fine, up. In both of these situations, your acceleration, spell that properly, is up. So when something is pushing upwards against you, this is when your normal, to accelerate up, the normal force upwards has to increase. That's when you're going to feel like you're heavier than you actually are. The 2 times that Vine you described feeling lighter was when we were going down from rest. Going down from rest, or going up and stopping. In both of these cases, the acceleration is which direction? If this one's dropping you from rest, or you're traveling up but coming to a stop, in both of these scenarios, the acceleration is downward. And the 3 times that all of a sudden you felt normal again were when? Should be 3 times here. There were 3 times when your experience of your weight should have normalized. Yeah? Okay. At rest, the elevator is not moving. What do you mean? Yeah, that's the at rest. That's the same scenario. Whether you're standing there at the top waiting to go down, at the bottom waiting to go up, I'll call those the same scenario. Yeah, the middle of the way through, whether you're traveling up or down. So moving up or moving down. At the middle part, what was happening? Why do you no longer feel heavier or lighter? If you felt heavier because you're accelerating upwards, or you feel lighter because you're accelerating downwards, when you don't feel anything other than what you normally experience of your weight, what has to be true about the moving up and down here? Sorry? Slowing down is over here. While moving down and slowing down, or moving up and slowing down, that's when you felt heavier. The in-between is actually when the elevator is at constant V. Constant V in both of these scenarios. So you feel what you actually weigh in these three scenarios when the acceleration equaled 0. You're either at rest or moving at a constant velocity. So when you're not accelerating upwards or downwards, that's when you start to experience, or that is when you are experiencing your actual weight equaling your apparent weight. So I'm going to do a couple examples of actually doing some calculations. We're going to do 5. Even though I've only got 4 here, we're going to add 1. Do I want to do 5? You know what? We might just change this bottom one. Here we go. So if you're a 65 kilogram person in an elevator, traveling upwards at 5 meters per second, what is your apparent weight? Now we're going to do each one of these in all of its painful detail, but you should see here already, if you're traveling upwards at 5 meters per second, you've got a constant velocity here. Your apparent weight should equal what? Sorry? 65 is your mass. What do you have to do to 65? What do you have to do to your mass to get your weight? Times 9.8. So they should be equal. So let's prove it. Here you are in an elevator. Short legs, long middle. There you are in an elevator. And you are moving up at 5 meters per second. So if you're going that way, 5 meters per second, what forces are acting on you? Not the elevator, you. Yeah, here it is. There's a normal force acting upwards, Fn, and there's Fg acting down. Now, because this is constant, if you're moving at 5 meters per second, acceleration equals 0. If acceleration equals 0, Fnet also has to equal 0. If Fnet equals 0, that means, well, let's call upwards positive. That means your upwards force minus your downwards force has to equal 0. So that means your Fn has to equal your Fg. So your Fn in this case, and Fn, the normal force, is equivalent to your apparent weight. Is just going to equal 65 times 9.8. That value is 637 newtons. But this is how you'd reason it through. I should have probably moved all that up. I would have had more space. Constant velocity, acceleration is 0. So your net force is 0. So these forces are equal, the sum of them, a positive and a negative, equals 0. So they're equal. Then we calculate. Okay, that same person is in an elevator that accelerates upwards at 4.9 meters per second squared. So half of the acceleration due to gravity. What is their apparent weight? So we have the same situation. Let's draw the elevator again. Let's put that person in the elevator again. Let's draw the forces acting on that person again. In each case, we've got an Fg downwards and an Fn upwards. But in this case, they're accelerating upwards. So there is an upwards acceleration, A equals 4.9 meters per second squared. I'm going to call that upwards positive. That's the implication that I've given it here. So to figure out their apparent weight is the same thing as asking you to find their normal force. So we've got a mass this time. Sorry, we've got an acceleration this time. So So F net equals ma. So because I've called our upwards acceleration positive, that means Fn is going to be positive and Fg is going to be negative. So Fn minus Fg is going to equal ma. And now I can just plug everything in. Fn, the apparent weight, minus 65 times 9.8 equals the mass of the person times their acceleration. They're accelerating at 4.9 meters per second squared, so that's going to be 65 times 4.9. And we can isolate this thing for Fn. Fn is going to be 65 times 4.9 plus 65 times 9.8. So they're going to experience themselves as having an apparent weight of, if you do the math here, 955.5 newtons. How does this value relate to that value? What are they experiencing? What does your gut tell you? We're even looking at the values for the accelerations. If this is the acceleration for the elevator, that's half of gravity. So if we add these two together, we're going to get the 4.9 plus the 9.8 is going to be 1.5 times gravity. This person is experiencing in the elevator while the thing's accelerating what it would be like to spontaneously gain half their mass, which would be weird. Okay, let's do one more. Well, I'm sure it'll be two more. So the elevator is reaching the top and then decelerates at 4.9 meters per second squared. So we're losing apparent weight in this example. You've got an object, we're still in the elevator. Here you are. We still have an Fg acting downwards and an Fn acting upwards. But in this case, what's the acceleration? If you're decelerating while you're moving upwards, acceleration is which way? Acceleration is down. So there's a downwards acceleration. That value is 4.9. In the previous one, I called up positive. Do we care what we call positive here? Do you want to call down positive in this case? Or do you want to call up, or do you want to still maintain up being positive? You still want up to be positive? Okay, so then if up is positive, this downwards acceleration needs to be explicitly negative. Negative 4.9 meters per second squared. So then again, figuring out their apparent weight, we've got an acceleration. Apparent weight is just your experience of your normal force. So F net equals ma. Down is negative, so this upwards Fn is still positive. It's going to be Fn minus Fg equals ma. Fn minus 65 times 9.8 equals 65 times negative 4.9. We're calling down negative, so that acceleration needs to be in there as negative. So then solving this thing for Fn, we're going to add this thing over to the other side, and we're going to get 65 times negative 4.9 plus 65 times 9.8. When they were accelerating upwards, you said this is when they felt heavier. This is what we experienced mathematically. So as they're decelerating up, they should feel lighter. This is negative. It's going to take away from this guy here. And we're going to, this person, whoever they are, is going to experience their weight at 318.5 newtons, or half of what they actually weigh. So what they would experience for this brief deceleration, however long it takes to decelerate at this rate, if this was you, you would experience yourself as spontaneously losing half your mass, which would be weird. But that's what it would feel like. All of a sudden, you are half your mass for as long as it takes to decelerate. Now, I'm going to change this bottom one here. We're going to use the information that we got from here today standing on a scale, and rather than finding out what his apparent weight is when at this acceleration, we know what his apparent weight was. He was standing on a scale. It told us. So here today approximately weighs 140 pounds. We're going to convert all of this thing to kilograms here in a sec. I ballparked this. It seemed to me, and now you can dispute this if you'd like, but it seemed to me, watching the scale between his feet, that on the way down, when we were accelerating downwards towards the first floor, your weight dropped to 142 pounds-ish. It looked like you didn't make it to 140, but you were more than halfway, is what it looked like to me. And then on the way back up, the same kind of thing. You didn't make it all the way to 160, but you were more than halfway. I called that 158. Does anyone want to dispute these values, or you all kind of felt the same thing? Here today? I mean, if we're going to get really, yes, but is this the swing you experienced? I'm not saying you normally, I don't know if you weigh 150. You don't weigh 150. Because if we're going to be clear, if you wanted to actually weigh yourself, you'd do it naked. We're not going to do that because that would be inappropriate at school. I don't want to weigh your jeans and your shoes and your hoodie. But for you, in your state, this was your weight. This is the more important thing. Do you feel like this was an appropriate swing? Okay, so let's use this information. We're going to use this information to actually figure out what is the acceleration of that elevator. So we've got here day. Here day at rest was approximately equal to 150 pounds. We're going to convert that to your mass. The conversions, does anyone know the conversion from pounds to kilograms? Yes, 1 kilo is 2.2 pounds. So to go the other way, we're going to take your pounds and we're going to divide by 2.2. 150 divided by 2.2 gives you a mass of, I don't like that number. If I do this, does it give me a better number? Nope. Now let's use it. 68 kilos. It had a bunch of decimals, so let's round them away. 150 pounds is approximately 68 kilograms. When we were accelerating upwards acceleration, your apparent weight changed to 158 pounds, which, 158 divided by 2.2. 72 kilograms. And when we were accelerating downwards, your weight was 142. The floor of the elevator was trying to get away from you. So you experienced a lesser normal force. 2 is, boom, 64.5. So these were your apparent masses at rest. We can turn these into right, here we go. This guy here is equivalent to FG. This is you at rest. So I'm going to take our 68 kilograms, and we're going to multiply that by 9.8. 68 times 9.8. This is you at 666 newtons. That's FG. This is what you experienced your mass to be. So if I take this 72 kilograms and I multiply that guy by 9.8, this value here, your 705.6 newtons, this is not your FG, because we're not at rest anymore, we're accelerating. This is your Fn on the way up. And then your Fn on the way down is your experience of your mass, your 64.5 times 9.8 is 632. That's your Fn on the way down. Using these values, we can actually figure out what the acceleration of that elevator is. So, we want to find the upwards acceleration. And it looks exactly like this calculation. We've got F net equals MA. So if we're going to call up positive, which I think is reasonable, we're going to have an Fn minus Fg equals MA. So down here in the limited space that I don't have, I'm going to jump straight from this line to this line, but I'm going to plug in these values. Your normal force on the way up, you experience to be 705.6 newtons. Minus your Fg. Your Fg is your mass at rest, the 666 newtons. Sorry, or your weight at rest, 666. And that's going to equal your mass. Your rest mass is 68 times A. So then the acceleration of this elevator is just going to be these two subtracted divided by here day's mass. 705.6 minus 666 divided by here day's mass. And we get an acceleration of 0.6 meters per second squared. So comparing your experience in that elevator with these three examples here, a 4.9 meter per squared acceleration, your experience is very different from what this person would be experiencing. This person's experience is like 8 times your experience. Likewise, if I wanted to find the acceleration downwards, now presumably the acceleration downwards is going to be the same. Let's figure it out. The downwards acceleration, if we set it up the exact same way, F net equals FA, you guys wanted to call downwards, well, here today wanted to call downwards negative. So we still had the same setup. It was Fn positive minus Fg. So Fn in this case is 632. Your Fn on the way down. Minus your Fg was 666. Equals your mass, 68 kilograms, times A. So 632 minus 666 divided by 68. This is actually negative 0.5 meters per second squared equals A, based on those values. There you go. We found the acceleration of the elevator and the Sweeney Center. Questions, comments, concerns about anything I've done here? Okay, then that's it for today. We're gonna save inclines to tomorrow. They're involved. So this is the page I want you to take a look at. There's a bunch of questions here. There's 12 of them. It gives you a scenario up at the top. Imagine you're standing on a bathroom scale in an elevator, like here they just was, and you're holding an apple. You weigh 500 newtons. That's a weight. So your mass is about 50 kilograms. And then it walks you through a set of scenarios. You just board the elevator. You're inside it at rest. I want you to go through this whole set of scenarios. Well, it's one big scenario, but the 12 questions associated here, that's it. That's what I want you to take a look at today. Once you finish that, it's only 20 after 10. You have about about 35 minutes to lunch. If you finish that, you can use whatever time is left for your continue making progress on those 2 labs that you have to hand in to me, the spring lab and the friction lab. But the rest of the class is yours. On your mark, say giver.